Hey guys, welcome to Edge of Mind. Tonight we're going somewhere strange. We're going to explore time travel. Not the kind from movies with glowing machines and countdowns, but something quieter than that, something real. You might be surprised to learn that time travel isn't science fiction, it's science fact. And by the end of tonight, you'll understand why. Before we talk about how time bends and stretches, let me tell you how humans first learned to measure it. For most of history, people tracked time by watching the sky. The sun rising and setting marked the days. The moon growing full and fading again marked the months. The slow wheel of stars across the seasons marked the years. This was enough for a long time. Farmers knew when to plant. Sailors knew when to expect tides. Everyone knew roughly when to sleep and when to wake. Ancient Egyptians built sundials carving marks into stone and watching shadows creep across them as the hours passed. But these hours were not equal. Summer hours were longer than winter hours, because daylight was simply divided into 12 parts, no matter how long the day actually was. Water clocks offered something more consistent. A vessel with a small hole would drain at a steady rate, and markings on the side showed how much time had passed. The ancient Greeks used them. The Chinese used them. For centuries, dripping water was one of the best ways to track time. Mechanical clocks appeared in medieval Europe, using falling weights to drive gears. Church towers housed large clocks that rang bells to mark the hours, and for the first time, entire towns shared the same sense of time. Pendulum clocks came in the 17th century. The regular swing of a pendulum, back and forth, provided a steady heartbeat for the mechanism. For the first time, clocks could be accurate to within seconds per day. Quartz clocks came in the 20th century, using the vibration of quartz crystals to keep time. These vibrations are incredibly steady, far more reliable than any pendulum. Eventually, quartz clocks became cheap enough for wristwatches and kitchen walls, and then came atomic clocks, measuring time based on the vibrations of atoms themselves. Atoms vibrate with such perfect consistency that the best atomic clocks today would not gain or lose a second in hundreds of millions of years. This extraordinary precision revealed something unexpected. Time itself is not as constant as our ancestors assumed. The better we measure it, the more we discover its strange behavior. If you're new here, I'd love to know where you're watching from tonight. Drop a comment below. And if you're enjoying these calm explorations, consider subscribing so you don't miss the next one. Now let me tell you something that might surprise you. You're already traveling through time right now. We all are. We move through time at a rate of 1 second per second, always forward, never stopping. That might sound obvious, but it raises a question that has puzzled humans for thousands of years. What exactly is time? And why does it only seem to flow in one direction? Ancient philosophers debated whether time was even real. Some argued that only the present moment exists, that the past is gone and the future has not arrived, so neither is truly real. Others argued that time is like a river, flowing from past to future, carrying everything with it. Modern physics has revealed that time is stranger than either view suggested. Time is not a river flowing at a constant rate. It's more like a fabric that can stretch and compress and bend. And this is not a metaphor. This is what actually happens. Time does not move at the same speed everywhere. For most of human history, people assumed time was constant. A second was a second, everywhere, for everyone. The clock on your wall and the clock on a distant star would tick at exactly the same rate. Time was the great equalizer, the one thing that treated everyone the same. Albert Einstein proved this was wrong. In 1905, a young patent clerk in Switzerland published a paper that would change our understanding of the universe forever. It contained a stunning prediction. Time moves slower for objects that are moving fast. Time itself slows down when you move quickly. Not just clocks, not just perception. Time itself. This is not a guess. It has been measured thousands of times with extraordinary precision. Moving clocks tick slower than stationary ones. The faster you move, the slower your time passes compared to someone standing still. This effect is called time dilation, and it means that time travel into the future is not only possible, it's happening right now. Astronauts on the International Space Station are traveling through time. Right now, as you listen to this, there are human beings orbiting Earth at about 28,000 kilometers per hour. And because of their speed, time is passing slightly slower for them than for you. After spending 6 months in space, an astronaut returns to Earth having aged about 0.007 seconds less than everyone else. That's not much. It's a tiny fraction of a second. But it's real, it's measurable, and it proves something profound about the nature of reality. Time is flexible. The thing we thought was constant, the thing we thought treated everyone equally. It bends, it stretches, it changes depending on how fast you move. If we could build a spacecraft that traveled much faster, the effect would become dramatic. Imagine a ship that could travel at 90% the speed of light. At that velocity, time dilation becomes significant. For every year that passes on the ship, about 2.3 years would pass on Earth. Now imagine traveling at 99% the speed of light. For every year on the ship, about 7 years would pass on Earth. You could leave home, travel for what feels like 12 months, and return to find that 7 years have passed for everyone you left behind. At 99.9%, the speed of light, the ratio climbs even higher, about 22 to 1. 1 year of your life would equal 22 years back home. This is not speculation. This is what the equations of special relativity predict, and every experiment we have ever conducted confirms it. The universe allows time travel into the future. The only question is how fast we can go. But speed is not the only thing that affects time. Gravity does too. And this is where things become even stranger. Einstein published another theory in 1915, his general theory of relativity. It revealed something remarkable. Time moves slower in stronger gravitational fields. Near a massive object like a planet or a star, time literally passes more slowly than it does far away in empty space. The stronger the gravity, the greater the effect. Think about what this means. Your feet are slightly closer to the center of the Earth than your head. They experience slightly stronger gravity. Time passes slightly slower for your feet than for your head. The difference is incredibly small, far too small to notice, but it's real. And with precise enough instruments, it can be measured. Atomic clocks placed at different altitudes show measurable differences. A clock at sea level ticks slightly slower than a clock on a mountaintop. Not because the clock is broken, but because time itself flows differently depending on how deep you are in a gravitational field. The first test of gravitational time dilation was performed in 1959. Physicists Robert Pound and Glenn Rebka worked in a tower at Harvard University. They measured how gravity affected the frequency of gamma rays traveling up and down the tower. The experiment confirmed Einstein's prediction exactly. Gamma rays climbing up the tower lost energy. Gamma rays falling down gained energy. The shifts matched the predicted gravitational time dilation perfectly. Since then, the effect has been measured with increasing precision. Modern atomic clocks are sensitive enough to detect time dilation over height differences of just a few centimeters. If you move an atomic clock from the floor to a table, time speeds up measurably. This is not theoretical physics. It affects technology you use every day. GPS satellites have to account for gravitational time dilation constantly. The satellites orbit about 20,000 kilometers above Earth, where gravity is weaker. Their clocks tick faster than clocks on the ground by about 45 microseconds per day. That might sound insignificant, but if GPS systems did not correct for this time difference, your position would drift by about 10 kilometers per day. The system would become useless within hours. Every time you use GPS navigation, you're relying on corrections for relativistic time dilation. Einstein's theories are not just beautiful ideas. They're built into your phone. The global positioning system is perhaps the most practical application of time dilation. It demonstrates that relativistic effects are not just laboratory curiosities. They're engineering requirements for modern technology. Each GPS satellite carries atomic clocks that must be corrected for two different relativistic effects. First, the satellites move at about 14,000 kilometers per hour relative to the ground. This speed causes their clocks to tick slower by about 7 microseconds per day due to special relativistic time dilation. Second, the satellites orbit at about 20,000 kilometers altitude where gravity is weaker. This causes their clocks to tick faster by about 45 microseconds per day due to general relativistic time dilation. The two effects work in opposite directions. The velocity effect slows the clocks. The gravitational effect speeds them up. The net effect is that satellite clocks tick faster than ground clocks by about 38 microseconds per day. This must be corrected or navigation errors would accumulate rapidly. The correction is built into the satellites themselves. Before launch, their clocks are adjusted to run slightly slow, so that once in orbit, they tick at the same rate as clocks on the ground. Additional corrections are applied by the receivers. Without these relativistic corrections, GPS would fail within hours. Position errors would grow by about 10 kilometers per day. The system would become useless for navigation. Every GPS fix you receive has Einstein's physics built into its calculations. Relativity is not abstract theory. It's engineering necessity. This practical application of time dilation affects billions of people every day. Airplanes navigate using GPS. Ships cross oceans using GPS. Emergency services locate people using GPS. Farmers guide their tractors using GPS. Surveyors measure land using GPS. The modern world depends on satellites whose clocks must be corrected for effects that Einstein predicted over a century ago. It's one of the most beautiful connections between pure physics and practical technology. A black hole is a region where gravity is so strong that nothing can escape, not even light. Near a black hole, time slows dramatically compared to time far away. If you could orbit close to a black hole without falling in, time would pass much slower for you than for someone watching from a safe distance. You might experience an hour while they experience a year, or a decade, or a century. It depends on how close you get. The closer you get to the event horizon, the boundary of the black hole, the slower time moves. At the event horizon itself, time appears to stop completely from the perspective of a distant observer. Imagine watching someone fall toward a black hole. As they approach the event horizon, you would see them slow down. Their movements would become sluggish. Light from them would shift toward red as time dilation stretched the wavelengths. They would appear to freeze at the edge, never quite crossing, fading gradually as their light red shifted into invisibility. But from the falling person's perspective, nothing special happens at the event horizon. They would cross it in finite time by their own clock, falling onward toward the center. This strange disagreement between perspectives is one of the most unsettling features of general relativity. Two observers can experience time so differently that events which seem to take forever for one happen quickly for the other. Time is not a single universal flow. It is deeply personal, shaped by where you are and how you move. This extreme time dilation near black holes has inspired countless science fiction stories. In the movie Interstellar, astronauts visit a planet orbiting close to a black hole. They spend a few hours on the surface. When they return to their ship, they discover that 23 years have passed. The crew member who stayed behind has aged while they remained young. This is not fantasy. This is what Einstein's equations predict. Time dilation near a black hole can be that extreme. The movie consulted physicist Kip Thorne to ensure the physics was accurate. The time dilation depicted in the film is real, based on actual calculations of how time behaves near rotating black holes. There's a famous thought experiment that illustrates time dilation in a vivid way. It's called the twin paradox. Imagine two twins. One stays on Earth. The other boards a spacecraft and travels to a distant star at 99% the speed of light, then turns around and comes back. The journey might take 40 years by Earth's clocks, but aboard the ship where time is moving more slowly, only about 6 years would pass. The traveling twin would return younger than the twin who stayed home. This is not a trick or an illusion. It's a real prediction of relativity, and versions of this experiment have been confirmed with atomic clocks on airplanes and satellites. Time genuinely passes at different rates depending on motion and gravity. The twin who travels returns younger. Their body aged less. Their heart beat fewer times. They experienced fewer moments, and yet both perspectives are equally valid. There is no absolute frame of reference, no cosmic clock that determines which twin experienced the real passage of time. This might seem paradoxical, but it's the way the universe works. Time is relative. It bends. It stretches, and it creates outcomes that feel impossible, but are mathematically inevitable. Now let's talk about the question that haunts most discussions of time travel. Can we travel backward in time? Can we visit the past? The answer is complicated. According to our current understanding of physics, traveling backward in time is far more difficult than traveling forward. In fact, it may be impossible, but the door is not entirely closed. General relativity, Einstein's theory of gravity and spacetime, allows for certain solutions. Backward time travel could theoretically occur in these cases. These solutions involve exotic structures called closed time-like curves, paths through spacetime that loop back on themselves, allowing an object to return to an earlier point in its own history. One example is the rotating black hole, also called a Kerr black hole. When a black hole spins, it drags spacetime around with it, creating a region where strange things become possible. In principle, you could enter this region, follow a particular path, and emerge before you entered. You would have traveled backward in time, but there are enormous practical problems. The interior of a black hole is lethal. The tidal forces would tear you apart. And even if you could survive, the mathematics suggest problems. The region allowing backward time travel might be unstable or inaccessible from the outside universe. Another theoretical possibility is the wormhole, a tunnel through space-time connecting two distant points. If one end of a wormhole moved at high speed while the other remained stationary, time dilation could cause the two ends to experience time at different rates. In theory, you could enter one end and emerge from the other at an earlier time. But wormholes, if they exist at all, would require exotic matter with negative energy density to hold them open. We have never observed such matter, and it may not exist. Even if it does, creating and maintaining a stable wormhole large enough for a human would require technology far beyond anything we can currently imagine. Some physicists have proposed another route to the past, one that involves cosmic strings. These are hypothetical, one-dimensional defects in spacetime, left over from the early universe. If two cosmic strings passed by each other at nearly the speed of light, they might create a region where backward time travel becomes possible. But like wormholes, cosmic strings are speculative. We have never detected one. And even if they exist, using them for time travel would require manipulating objects of immense mass and energy on a cosmic scale. All of these possibilities share a common feature. They are permitted by the equations of general relativity, but they require conditions so extreme, so exotic, and even if they were, they raise deep questions about causality and paradox. What happens if you travel back in time and prevent your own birth? This is the famous grandfather paradox. If you succeed, then you were never born, so you could not have traveled back in time, so you could not have prevented your birth. So you were born after all, so you could travel back in time. The logic loops endlessly. Some physicists have proposed that the universe might prevent such paradoxes through self-consistency. Any action you take in the past must have already been part of history. You cannot change what happened. You can only fulfill it. If you travel back in time, you were always there. History is a single self-consistent loop. Others suggest that traveling to the past might create a new branch of reality, a parallel timeline, where events unfold differently. In this view, the grandfather paradox is avoided because the past you affect is not the same past you came from. Your original timeline remains intact. You have simply created or entered a new one. But these ideas remain speculative. We have no experimental evidence for backward time travel. We have no confirmed examples of paradoxes resolved through self-consistency or branching timelines. For now, it remains a fascinating puzzle at the edge of physics. There's another strange consequence of relativity that touches on time travel. It's called the relativity of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another observer, moving at a different speed. Imagine two lightning strikes hitting opposite ends of a train platform at the same moment, as measured by someone standing still on the platform. To that observer, the strikes are simultaneous. But to someone on a moving train, the strikes would not be simultaneous. Depending on the train's direction and speed, one strike would appear to happen before the other. This is not an optical illusion. It's a fundamental feature of space-time. There is no absolute present moment that extends across the universe. Different observers, moving at different speeds, will disagree about which events are happening now. This means that now is not a universal concept. Your present moment is not the same as someone else's present moment, if you are moving relative to each other. The universe does not have a single shared present. It has many overlapping presents, each valid in its own frame of reference. This idea is deeply strange. It suggests that the past, present, and future all exist in some sense, laid out in the four-dimensional structure of space-time. You are not moving through time like a boat on a river. You are a path through space-time, a sequence of events that already exists as a pattern in the fabric of the universe. Some physicists call this the block universe view. All of space-time, from the beginning to the end, exists as a single unchanging structure. The flow of time, the sense that the present is special, is an illusion. It's created by our consciousness as we experience one moment after another along our path through the block. This view is unsettling. It suggests that the future already exists, laid out and unchangeable, waiting for us to reach it. It suggests that free will might be an illusion, that every choice we think we make has already been made, already written into the structure of space-time. But not all physicists accept the block universe view. Some argue that the present is genuinely special, that the future is open and undetermined, and that the flow of time is real, not illusory. The debate continues, quiet and unresolved, at the heart of physics. Now let me tell you about one more strange feature of time. It's called time's arrow. This is the observation that time seems to have a direction. Events unfold from past to future, never the other way around. You can scramble an egg, but you cannot unscramble it. You can watch a glass shatter, but you cannot watch the pieces leap back together and form a whole glass again. Entropy, a measure of disorder, always increases over time. This is the second law of thermodynamics, and it gives time its arrow. But here's the puzzle. The fundamental laws of physics are time-symmetric. If you recorded a video of particles colliding and played it backward, the backward version would still obey the laws of physics. There's nothing in the equations that says time must flow in one direction. So why does the universe have an arrow of time? Why does entropy increase? Why do we remember the past but not the future? The answer seems to lie in the initial conditions of the universe. The Big Bang created a state of extremely low entropy, a highly ordered beginning. Since then, the universe has been evolving toward higher entropy, greater disorder. We experience this evolution as the flow of time. But this raises another question. Why did the universe begin in such a low entropy state? What set the initial conditions? We don't know. It remains one of the deepest mysteries in cosmology. Some physicists speculate that the arrow of time might reverse if the universe eventually stops expanding and begins to contract. In a collapsing universe, entropy might decrease. Events might unfold backward. But this is highly speculative. Most evidence suggests the universe will expand forever, carrying its arrow of time forward into an endless future. For now, time flows in one direction, from past to future, from order to disorder, from birth to death. And we flow with it, carried along by the current we cannot escape. There are other strange ideas about time that physicists have explored. One is the possibility that time might not be fundamental. Just as temperature is not a fundamental property, but emerges from the motion of particles, time might emerge from something deeper. Some theories of quantum gravity suggest that at the smallest scales, space and time might dissolve into something more abstract, a network of relationships, a pattern of information, a quantum foam where the usual rules of space-time break down. In this view, time as we know it is an approximation, a useful concept that applies at large scales but loses meaning when you zoom in close enough. The universe at its deepest level might be timeless, and the flow of time we experience might be a consequence of our limited perspective, our inability to see the full structure. These ideas are speculative. We don't have experimental evidence for them, but they hint at the possibility that time is not what it seems. The familiar ticking of clocks and the march of moments might be shadows of something stranger and more fundamental. And now let's turn to a question that feels more human. If time travel were possible, if we could journey to the past or leap into the future, what would it mean for our lives? Imagine traveling forward in time. You step into a machine, close your eyes, and when you open them, 100 years have passed. Everyone you knew is gone. The world has changed beyond recognition. Technology, culture, language, everything is different. Would you feel like a visitor, a ghost from another era? Would you be able to adapt, to find your place in a world that moved on without you? Or would you be forever out of step, longing for the time you left behind? And what about traveling backward? Imagine visiting the past, walking through a world that no longer exists, seeing people who have been gone for generations. Would it bring comfort or grief? Would you want to change things, to fix mistakes, to warn people of what's coming? Or would you accept the past as it was, knowing that any change might unravel the present you came from? Time travel, if it were possible, would not just be a technological achievement. It would be an emotional and philosophical challenge, forcing us to confront our relationship with time, with memory, with loss. But for now, time travel remains theoretical. We move through time in only one direction, at one speed, carried by the river we cannot escape. And maybe that's enough. Maybe the present moment, fleeting and irreplaceable, is all we need. Time has a strange relationship with our perception. Sometimes a minute feels like an hour. Sometimes an hour feels like a minute. When you're bored, time drags. When you're engaged, time flies. When you're in danger, time seems to slow down, allowing you to process events in what feels like slow motion. These experiences are not time dilation in the physics sense. Your clock is still ticking at the same rate. But your brain's processing of events changes, creating the subjective sensation that time has stretched or compressed. Scientists have studied this phenomenon. When people experience high adrenaline situations, they often report that time seemed to slow down. Researchers believe this happens because your brain records more memories during intense moments. When you later recall the event, the density of memories makes it feel like more time must have passed. Time perception also changes with age. Children often feel that time moves slowly. A summer vacation feels endless. A year feels like forever. But as you get older, time seems to accelerate. Years slip by more quickly. Decades blur together. One explanation is that each year represents a smaller fraction of your total life. When you're 5 years old, 1 year is 20% of your entire existence. When you're 50, 1 year is only 2%. The proportion shrinks, and time feels faster. Another explanation involves novelty. Children experience new things constantly. Every day brings new sights, new words, new concepts. The brain encodes these novel experiences richly, creating dense memories. Adults, living in familiar routines, experience less novelty. Days blend together. Fewer distinct memories form, and time seems to pass more quickly because there are fewer mental landmarks to mark its passage. Time also feels different in different states of consciousness. In dreams, time becomes fluid. Hours can seem to pass in minutes, or minutes can stretch into what feels like hours. You can experience entire lifetimes in a single night's sleep. Meditation can alter time perception too. Experienced meditators often report that time seems to slow down or even disappear during deep practice. The usual sense of duration, of past flowing into future, fades away. Only the present moment remains, expanded and timeless. These subjective experiences remind us that time is not just a physical phenomenon, it's also a psychological one. We don't just exist in time, we experience it, interpret it, give it meaning. And yet, beneath all these subjective experiences, the physics of time continues, steady and indifferent. Your clock ticks at the same rate whether you're bored or fascinated, young or old, awake or dreaming. Time doesn't care about your perception. It flows according to the laws of relativity, shaped by motion and gravity, immune to your feelings about it. This creates a strange duality. Time is both deeply personal and utterly impersonal. It's the most intimate aspect of your existence, and the most cosmic. It's what you experience moment by moment, and what governs the movement of galaxies. There are places in the universe where time behaves in ways we can barely imagine. Near the edge of a black hole, time dilation becomes so extreme that the universe outside appears to speed up dramatically. If you could somehow survive near the event horizon and look outward, you might see something extraordinary, stars being born and dying in what seems like fast forward. Galaxies would wheel across the sky. Eons would pass in what feels like hours. But you would not perceive anything strange about your own time. Your heartbeat would feel normal. Your thoughts would flow at their usual pace. The strangeness would only be apparent when you compared your experience to the universe outside. This is one of the deep lessons of relativity. There is no privileged frame of reference. There is no cosmic clock that determines the true rate of time. Every observer's experience of time is equally valid, equally real. The universe doesn't care which perspective is right, because they're all right. Time is what each observer measures it to be. The disagreements between observers are not errors or illusions. They're features of space-time itself, woven into the fabric of reality. There are also cosmic events that help us understand time's nature. Supernovae, the explosive deaths of massive stars, emit light that travels across vast distances. When we observe a supernova, we're seeing an event that happened long ago. The light has been traveling through space for years, centuries, or even millennia before reaching our eyes. In a sense, when you look at a distant supernova, you're looking backward in time. You're seeing the past preserved in light, arriving at your eyes tonight. The star that exploded might not even exist anymore. It might have collapsed into a black hole or dispersed into a nebula, but its light continues to travel, carrying information about an event that happened in a different era of the universe. This is true for everything you see in the night sky. The stars you look at tonight are not as they are now. They're as they were when their light left them. Some of the stars you see might have already died, their light still journeying across space toward Earth. We live in a universe where the past is always visible, always arriving, always overlapping with the present. When you look at the stars, you're looking at a mosaic of different times, different moments, all coexisting in the night sky. Even the sun, our closest star, shows us the past. The light from the sun takes about 8 minutes to reach Earth. When you feel warmth on your face, you're feeling energy that left the sun 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. For those 8 minutes, we would continue to see it shining in the sky, unaware that it was already gone. Light has a speed limit, and that speed limit means we can never see the present moment of anything distant. We can only see the past. The farther away something is, the further back in time we see it. The most distant galaxies we can observe are so far away. Their light has been traveling for billions of years. We see them as they were when the universe was young, when stars were first forming, when galaxies were just beginning to take shape. In this way, telescopes are time machines. They don't let us travel through time ourselves, but they let us look backward, to see the universe as it was long ago. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, shows us the universe as it was about 13.8 billion years ago. That's just 380,000 years after the beginning. That radiation has been traveling through space ever since, cooling and stretching as the universe expanded. When we detect it today, we're seeing an image of the infant universe, a snapshot from the very edge of time. It's the oldest light we can ever hope to see, a relic from an era when there were no stars, no galaxies, only hot plasma slowly cooling into transparency. This is one of the most profound aspects of astronomy. We don't just study space, we study time. Every observation is an observation of history. Every photon carries a message from the past. There's a concept in physics called proper time. This is the time measured by a clock that travels with an object, the time experienced by the object itself. Proper time is always the shortest time between two events along any possible path through space-time. This means something interesting. If you want to experience the maximum amount of time between two events, you should remain stationary and in a weak gravitational field. Any motion or exposure to stronger gravity will reduce the amount of time you experience. In a strange way, the universe rewards stillness. The more you move, the less time you experience. The faster you go, the less you age. Motion through space trades off against motion through time. This creates a kind of cosmic speed limit on experience. If you traveled at the speed of light, you would experience no time at all. Your journey, no matter how far, would feel instantaneous. You would leave and arrive in the same moment, from your own perspective. This is why photons don't age. They don't decay. They exist outside of time, frozen in an eternal present, moving through space, but never through time. For objects with mass, there's always some motion through time. Even if you sit perfectly still, you're still aging, still moving forward through the time dimension of space-time. You cannot stop your motion through time. You can only adjust its rate by moving through space or entering a gravitational field. This interplay between space and time is one of the most beautiful aspects of relativity. They're not separate. They're aspects of a single unified structure. When you move through space, you're also changing how you move through time. The two are forever linked. Think about a photon emitted from a distant star. From the photon's perspective, if it had one, the journey is instantaneous. It leaves the star and arrives at your eye in the same moment. But from your perspective, the journey took years or centuries. The photon experienced no time, but you experienced all of it. This seems paradoxical, but it's just another example of the relativity of time. Different observers measure different durations for the same journey. Both measurements are correct. Both are real. The universe simply doesn't have a single answer to the question, how long did that take? The answer depends on who's asking. Time is also connected to entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases in a closed system. Things tend toward disorder. Heat flows from hot to cold. Practices expand to fill their containers. Structures break down over time. This increase in entropy gives time its arrow, its direction. We can tell the past from the future because the past had lower entropy. An unbroken glass has lower entropy than scattered shards. A living organism has lower entropy than the same atoms dispersed and decayed. The universe began in a state of very low entropy, highly ordered and uniform. Since then, it has been evolving toward higher entropy, greater disorder. Stars form and burn out. Galaxies drift apart. Energy spreads and dilutes. Eventually, in the far future, the universe might reach a state of maximum entropy, a condition called heat death. All energy will be evenly distributed. All temperature differences will be erased. No work will be possible. No stars will shine. No life will exist. In this distant future, time might lose its meaning. If there's no change, no flow from one state to another, can time still be said to pass? Some physicists speculate that in a state of maximum entropy, time becomes irrelevant. The universe reaches a kind of static eternity, unchanging and timeless. But that future, if it comes, is trillions of years away. For now, the universe is full of change, full of flow, full of time. Your own life is part of this flow. You are a temporary decrease in entropy, a local pocket of order in a universe trending toward disorder. Your body maintains its structure by consuming energy and exporting entropy. You eat food, extract energy, and release waste heat. You take in low entropy sunlight, stored in plants, and release high entropy heat into the environment. This process cannot continue forever. Eventually, your body's ability to maintain order will fail. Entropy will win. You will return to the universe, your atoms dispersed and recycled, joining the great flow toward equilibrium. But for now, while you're alive, you're a beautiful defiance of entropy. You're a pattern that persists, a structure that holds, a flame that burns against the darkness. Time also appears in quantum mechanics, the physics of the very small, in strange and puzzling ways. In quantum theory, particles don't have definite positions or velocities until they're measured. They exist in a state of superposition, occupying many possible states at once. But measurement collapses this superposition into a single outcome, and measurement takes time. This creates a puzzle. How long does collapse take? Is it instantaneous, or does it unfold over some finite duration? The equations don't give a clear answer. Some interpretations of quantum mechanics suggest that time might emerge from quantum processes. What we experience as the flow of time might be a consequence of quantum decoherence. That's the process by which quantum superpositions give way to classical definiteness. In this view, time is not fundamental. It's not woven into the deepest level of reality. Instead, it emerges from the behavior of quantum systems as they interact and entangle with their environments. This is a radical idea, and it's far from proven, but it hints at the possibility that time, like temperature or pressure, might be a large-scale approximation. It's useful for describing the world we experience, but not present in the universe's deepest structure. There's also the question of whether time had a beginning. According to the Big Bang model, the universe began about 13.8 billion years ago in an extremely hot, dense state. Before that moment, there was no space, no matter, no energy, and perhaps no time. If time itself began with the Big Bang, then it makes no sense to ask what happened before. There was no before. Time didn't exist yet. The question is meaningless, like asking what's north of the North Pole. But this raises deeper questions. How can time begin? How can there be a first moment? If time didn't exist before the Big Bang, what triggered it? What caused the universe to come into being? Some physicists propose that time might be cyclic. The universe goes through endless cycles of expansion and contraction. Each Big Bang is followed eventually by a big crunch, followed by another Big Bang. In this view, time has no beginning and no end. It simply loops, eternally recurring. Others propose that our universe might be one of many, part of a vast multiverse, where time behaves differently in different regions. In some universes, time might flow forward. In others, it might flow backward, or not exist at all. These ideas are speculative, beyond our current ability to test, but they reflect how deeply mysterious time remains, even after more than a century of relativity and quantum mechanics. We've learned that time is flexible, that it bends and stretches, that it's relative and observer-dependent. But we still don't fully understand what it is, where it comes from, or whether it's fundamental to reality. Time keeps its secrets, and maybe that's appropriate. Time is the dimension we live in, the medium of our experience. It's so close to us, so intimately part of our existence, we might never fully step outside it to see it clearly. There's a beautiful idea in physics called the light cone. For any event in space-time, the light cone divides all other events into three categories. There are events in the past light cone, events that could have influenced this event because light could have traveled from them to here. There are events in the future light cone, events that this event could influence because light could travel from here to them. And there are events outside the light cone, events that are too far away for light to have traveled between them and this event. These events are called space-like separated. They cannot influence each other. They exist in a kind of mutual elsewhere, neither past nor future, but simply disconnected. Your light cone is the structure of what you can know and what you can affect. The past light cone contains all the events that could have shaped your present moment. The future light cone contains all the events you could possibly influence. Everything outside your light cone is beyond your reach. At least for now, you cannot affect it, and it cannot affect you. Not until your light cones overlap. This creates a kind of cosmic horizon around each event, a boundary between what's accessible and what's not. And that boundary is determined by the speed of light, the universal speed limit that connects space and time. In a way, the light cone is your place in the universe, your connection to the rest of space-time. It defines your past, your future, and your elsewhere. It's a geometric structure, but it's also deeply personal. Every conscious being has their own light cone, their own sphere of possible influence and knowledge. And as you move through time, your light cone moves with you. Events that were once in your future enter your present and then recede into your past. Events that were once beyond your reach gradually come into view. Your light cone is always shifting, always growing, always including new regions of space-time. You're not separate from the universe. You're embedded in it, connected to it through the structure of causality and light. There's also something poetic about the fact that light connects us across time. When you look at a star, you're seeing it as it was when the light left it, but in a sense, you're also touching it. The photons that enter your eye came from that star. They traveled across space and time to reach you. In that moment of seeing, you and the star are connected. The light is a bridge, a thread of causality linking you to something distant and different. And when you look at the night sky, you're seeing hundreds, thousands, millions of these connections. Each point of light is a thread reaching back through time, linking you to an event that happened years, centuries, or millennia ago. The sky is not empty. It's full of connections, full of light, full of the past arriving in the present. Time travel, in a sense, is all around you. You just have to look up. There are practical consequences to time dilation that affect modern life in surprising ways. Particle accelerators also demonstrate time dilation dramatically. When particles are accelerated to speeds close to the speed of light, they experience significant time dilation. Musons, for example, are particles created in Earth's upper atmosphere when cosmic rays strike air molecules. Musons are unstable and decay quickly, with a half-life of about 2 microseconds. At the speed muons travel, even without time dilation, they should only be able to travel about 600 meters before decaying. They shouldn't be able to reach the ground, but they do reach the ground in large numbers. The reason is time dilation. From our perspective, the muons' clocks are running slow. Their 2 microsecond lifespan is stretched out, allowing them to travel much farther before decaying. From the muon's perspective, its clock is running normally, but the distance to the ground is contracted. Length contraction, another consequence of special relativity, shrinks the distance so the muon can reach the ground in its short lifetime. Both perspectives give the same result. The muon reaches the ground, but they describe the journey differently. One invokes time dilation, the other invokes length contraction. Both are correct. This is another example of how relativity works. Different observers describe events differently, using different combinations of space and time. But they all agree on the outcomes, on what actually happens. The universe is consistent, even though different observers see it differently. Time also connects generations. Your parents lived in their own present moments, experiencing time at their own pace. Their parents before them did the same. And so on, back through history, an unbroken chain of people experiencing time, one moment after another. You're part of that chain. When you were born, you entered the flow of time that's been running since the beginning. And when you have children, if you choose to, they'll enter that same flow, continuing forward into a future you won't see. This is how time connects us, not just across space, but across generations. We're all riding the same river, entering at different points, experiencing different stretches, but sharing the same fundamental journey from past to future. And the strange thing is, because of time dilation, we're all experiencing that journey at slightly different rates. An astronaut ages slower than their twin on Earth. Someone living at high altitude ages slightly faster than someone at sea level. These differences are tiny, but they accumulate. Over a lifetime, they might add up to fractions of a second. Not enough to notice, but enough to be real. We're all traveling through time together, but at our own individual paces, shaped by our motion and our position in Earth's gravitational field. It's beautiful in a way. We're together and separate, sharing the journey, but experiencing it uniquely. The universe is vast and old. Stars are being born and dying. Galaxies are colliding. Light is traveling across billions of light years, and all of it is happening in time, governed by the same laws that govern your breath. You're part of something immense, something ancient, something that will continue long after you're gone. But right now, in this moment, you're here, alive, aware, experiencing time in your own unique way, from your own unique perspective. And that's a kind of miracle. Out of all the possible paths through space-time, you're on this one. Out of all the possible moments, you're experiencing this one. The universe is unfolding, and you're part of that unfolding. You're a pattern in time, a process, a temporary arrangement of matter and energy that can think and feel and wonder. And for now, while you exist, time is yours. Your journey through it is personal and unmistakable. Everyone gets the same amount of time in their own frame of reference. No matter how fast you move, no matter how deep you sink into a gravitational field, your own clock always ticks at the same rate for you. 1 second per second. One heartbeat at a time, one breath after another. You cannot escape time, but you also cannot lose it. Every moment you experience is a full moment, rich and real, shaped by the unique path you take through space-time. And that's beautiful. In a universe where time bends and stretches, where clocks disagree and simultaneity is relative, your experience of time is still your own, personal, unmistakable, true. So as you drift off tonight, know that you are traveling through time. You are moving forward, 1 second per second, into a future that does not yet exist. And every moment of that journey is yours. The universe will keep turning. The stars will keep shining. Time will keep flowing in all its many forms. If you're still awake, another episode is waiting for you. I hope you sleep well and dream softly. Good night.